Okay. Hello, everyone. So let's talk about the logistic for next 3 weeks. Basically, right now we are at week 3. So these are the due date that you had for this week. These are the due date for this week. And then we are going to have lab 6 and assignment 6 and discussion in this week, where the due date going to be next week in week 7. Okay, don't be confused with that. So these are the due dates for next week. So next week, what we do, we are going to have module 7, and you're basically going to have some assignment, labs, and discussion, all right? So the due date for those coming next week gonna be in week 10. So the due dates are given in here. The assignment gonna be, when I upload the assignment, the due dates are basically gonna be set up properly according to this schedule. Okay, so next week we're gonna have a module 7 in here, module 7. And the week after here is marked as study break. And the week after that, you're gonna have midterm exam, right? So what do we do in these 2 weeks? So the plan for a week after next week, basically next week is module 7, so we're gonna hold on the normal lab meeting on Friday, and we're gonna have your video recording for module 7 uploaded. You're gonna have your discussion and everything. But a week after, in week 8, we're gonna have a study break. So the plan is for this week, you're going to have some quizzes. Ideally, I want to have 3 quizzes to be held on during that week. So where in these quizzes, you're gonna be practicing or seeing some questions that are related to midterm exam. So midterm exam gonna come at week 9. So I'm gonna prepare you for the exam in this week. So the 2 quiz is happening. I'm also thinking about 3rd one, but I'm not sure to do that or not, because I'm planning to have 1 quiz definitely on Tuesday and 1 quiz on Friday, so that you guys go through these questions and then practice these questions and try to answer those questions. One thing that I want to do for this quizzes basically count toward your final grade. But I want to give you some kind of bonus in these quizzes, and how I'm going to give you that. So I want to let you to have multiple attempts for your submission. Meaning what? Meaning that so you're going to have basically multiple choice question in your quizzes. Then, so for example, you do your calculation, go take a look at your, materials, and then you answer some of these questions, and then you submit it, right? Maybe there are like 10 questions, and then you get, for example, 8 of them right and 2 of them wrong, right? So it's not going to be your last attempt. So you're going to have 4 attempts. Okay, 4 is not a bad number, okay? So next time you check, okay, which question you get wrong, and then you go and do more study on that and try to find the proper answer for that to get the full credit. So you're gonna have 4 attempts. So do it wisely. My expectation is that everyone in these quizzes should be able to get 100, okay? So one thing I wanna ask you guys is that please do not do these quizzes like randomly. There are multiple choice, that's correct. You can do it like in 2 minutes or 5 minutes. This is correct, yes. But it's better to work out the answer for each question on a piece of paper. Go to your lecture material, search for it, do some programming, and fill the question. And once you make sure, then you go and enter your answer. So make sure to get 100 in these quizzes. 4 attempts is a good number. And then you're going to have your midterm exam. In your midterm exam, so you're also going to have some multiple choice questions. And you are going to have also 1 or 2 programming questions. So, what I want to do is probably going to give you maybe 2 hours for your midterm. So it's going to be limited. It's not going to be like kind of open-ended exam. The exam going to be held on in 2 hours. So make sure that you're available during these 2 hours to complete your midterm exam. And if you do well in your quizzes, then you're going to be fine doing the midterm exam. One thing else that I want to be considering for you guys as a bonus for these 2 weeks, for those of you that missed some assignments, some labs, I know that I've posted the solution for those, so, but I'm thinking that no one is going to take a look at the solution. If you haven't submitted that, please go there and work out your lab, work out your assignments, and try to resubmit. I'm going to reopen all these assignment and lab. It's going to be too much work for me, but I'm going to do that for you guys to kind of help you to get a good grade in this course. So I understand that some of you have some technical difficulties with your system during these, month and a half time. So right now, most of you get your system working, and it's a good time to go back and work on some of those unfinished work and complete it and submit it during these 2 weeks. Okay, that's a plan. And let's talk about the midterm exam day. So week 8 are the quizzes, gonna be the week after next week. And then the week come after, week 9, is time for your midterm. So, and when is that? Okay, so let me take a look at the calendar. Okay, now your October 2nd, next week is basically your module 7, a week after is your break. Okay, your midterm is going to be on Tuesday, 20th of October. Okay, so please set that up. The time is going to be between 9 and 11 a.m. So that's the time for the exam. I'm gonna be posting this into the Canvas. So try to save that and remember this time. So you're gonna have this exam and week basically 9 and 8 and 9. Okay, so midterm is happening on October 20th. A week before midterm, you're gonna have 2 or 3 quizzes to prepare yourself for the midterm. Perfect. Any question? All right. Midterm is open note, yes. Yes, Alex, you can redo the assignment and lab. So my intention is to give you this opportunity to get the high grade, a very good grade in this course. So as you can see, as we are moving forward, the complexity or the level of difficulty of the course kind of decreases, and the reason is that you guys getting used to use Linux and virtual machine and your systems, and knowing how to start writing a program and how to basically run it. So these are good, and right now we are in a good stage to do all this program. So we have question from Alex, says, what time was the lab on Tuesday, the 20th? we don't have lab on Tuesdays. No, okay, you meant the exam. So exam gonna be at 9 a.m. and it's gonna take for about like 2 hours. Okay, just make sure for the exam it's individual. Don't work with the partner, and you're gonna be signing an agreement saying that you are just following the rules of the university. Okay, great. Now we worked out the schedule for the next 2 weeks. Let's talk about this lab and see how we can complete this lab successfully. Okay, let me share a document. So here is module 6 lab. All right, what you want to do? You have 2 activities in this lab. 2 activities. So activity 6.1 and activity 6.2. So what you want to do in these 2 activities? You want to learn how to move data from one memory location to another memory location, from one memory location to registers, and from registers to memory. So basically, this was a topic of your lecture 6. So you have some familiarity with the memory management right now in assembly. Let me share a sample of memory layout for x86 architecture computing. So these are the 2 questions. So I want to quickly go through the memory layout. Tells you how these different memory segments in your assembly code, where the locations are, and how that memory layout is basically related to this lab. So I want to show you a very simple memory layout for now. So if you basically take a look at the different memory layout on the internet, you're going to be seeing different layouts with more details. So my intention is just giving you some ideas how memory are organized, not the very fine detail, just very high level. Let me see if I have that in here. So lab 6, yeah. Okay. All right. Okay, guys. If you remember, during the last lab, we talked about different segments in your assembly code. So if you remember, one of the segments was data segments, right? So let me write on this. Okay. So one of the segments was data segment. Remember that in your assembly code, you write segment, that data, and then you put your initialized data in there. For example, you define byte, like hello world, or define byte like printing messages, data, arrays and everything you can define in that section, right? And there was another segment in our code called .bss. We said segment.bss, and underneath that we use keywords like RESD, for example, reserved double word, reserved byte, and then define the number of memory units in that section. And we don't basically initialize them. And if you try to read those contents, it's going to be some random value stored in there. So the reason that we define them, we're going to be using them as like a temporary variables in our program. We're going to be reading something from, for example, keyboard or input output, reading something from input and put it there, and then take it from there, do some processing, and then put something back. So when you're writing the program, we don't know what the value is going to be. Therefore, we just define the memory location or the values, and then we use it during the program. And then another segment was .text. You remember I said it's the segment .text, and then you will start writing your assembly code under that segment .text. Here there are two new things over here. We are not going to use these two things explicitly in this program, just for your information. This is a memory layout for a system like x86 architecture, 32-bit system. So these are the addresses related to each memory location. For example, in here, you have one memory unit with this address, and then, for example, in here you have one memory unit in this address, and the addresses probably increase in this order. Okay, so this is going to be your heap. This is where your system use this memory location to store some data, and this is the segment, the stack segment. Basically use a stack segment when you call a function, you put the return address in there. So once you complete your function, then you pop up your return address, and basically you come back to your main program. And this part says that this part, unused memory. It doesn't mean that we don't use this memory. This section is shared between the heap up and the stack. A stack could grow up into this unused memory, and also heap could grow up, right? So this unused memory is available in there. Based on your program, the stack might use some part of it, and then the heap might use the other part left. So this unused memory is going to be dynamically used during the program between the heap and the stack. And basically, these are the main components of your memory layout. So how this is related to this lab? Okay, all right, so that is a good question. So in this lab, what we want to do, we want to basically put some data in here. So put some data in this data segment section. All right, define an array with 10 elements, put it in that section, and then define some variables in here in a .bss section, like 10 elements, right? 10 empty elements in here, and 10 initialized elements in here. So what we want to do, we want to read this element from the .data section and put them in here. So basically, we create some data, the data array in there, and then using our program, what we want to do, we want to take those data and copy it in the .bss section. And so once we copy that, then we want to print that result in the screen in reverse order. That's it. So this is our task for this lab. You're going to be learning how to read the data from one memory location and put it in another memory location, and how to read data from the memory and print it out. You have done probably this before, but we're gonna investigate this in more detail in this lecture. Okay, so let's go a bit deeper on this. I see some questions in the chat. This is a technical question. Please, if you see this error, use the discussion board to discuss it. So we can also have answer in here, but let's focus on this lab for now and not be distracted by that. We can put it on discussion board. Discussion board right now is open. So watch the discussion board. If the answer is not correct, you'll provide correct answer. Okay, let's go back to the lab again and see what we want to do, okay? So the lab asks you to define a location in the dot, dot basically data, so dot segment data, right? So in this memory location, it says that you initialize some array. I assume that the name is this one and the value is, for example, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1. So you have array of 10 elements, 10 elements. And you basically define your array, for example, like X and these 10 elements. And what we said that is important is that when you define your array, assume that each element in array takes 4 bytes. So this is your first byte. Second byte. Assume that we go from top to down, okay, and we store it in this way. But you can assume also the reverse order, but you need to keep track of the address, okay? Then here. So each of these, for now, we said that, okay, when you allocate the memory, assume that it's 4 bytes. Okay, 4 byte length. 4 byte length or 32 bits length, okay? So what it means is that, okay, you have, for example, address X 2000, and then you start creating this in the dot data section. Assume that this is a dot data section, right? You start storing your data. You said that, okay, assume simple case when you have only 0, 1 value. 0, 1 value only take 1 bit, but we want to create these allocation for cases that it also can accommodate 32 bits integer value or string. So for now, we take it simple. We said that, okay, each element takes 4 bytes. For example, 0, 0, 0, 0, and 0. And then you have your ones in here. Okay, my memory is getting a bit big. 1, 2, 3, 4, and 5. Okay, so this is the array that we create at the dot data section. And we said that, okay, put it in the section called dot BSS. Only 2s. Okay. So and assume that this part basically is your .bss. What you want to do, you want to basically take this and copy it in the .bss section, but there is one interesting requirement for it. So we said that, okay, if the order of your array is from 0 to 1, now when you copy this, you reverse the order. Meaning that, okay, if this is your first address, you create a place using reserve. Sorry. What's the keyword that you use? Reserve D. D means double one. Reserve D, for example, 10. Okay, for example, we call it Y, reserve D 10. So you create a place, an empty container of 10 elements in this section. So this is going to be your array goes for 10 elements, but they are, you can assume that they're empty, but in practice, they're having some uninitialized value, some random value, and we don't care. So what we want to do, we want to reverse order, meaning that if this is the last element in my .bss section and this is the one, I want to put it in the first location at .bss. So the first 5 going to come in here, and your 0 going to go after, okay? So once you copy it in here, then you start writing another function, basically use the print integer function, and print this result on the screen. So if this is your input starting from 0, let me use another color if I can. So if this is your screen start as 0, 0, 0, 0, then 1, 1, 1, 1, 1, then what you should print out on the screen is the reverse order, means that you print out 1, 1, 1, 1, 1, 0, 0, 0, 0, 0. So that's your task. You copy it from this section, put it in this section in reverse order, and then you print it out on the screen with the print function. Basically, for doing this, you need to use those techniques that you have learned so far, like jump, like loop, and checking the basically your counter, initializing counter with 10, and then start reading one by one until you finish these 10 elements. But something very, very important in here regarding the address, okay? So I want to ask you guys this question. If x2000, that's the address for this element, right? If this is the address for this element, what is going to be address for the next element? We have one answer. Please feel free to post your answer. One answer is 2002 from Juan. Okay, thanks, Juan. Anybody else? Any input? You can speak out as well. 2004, another answer. 2004. Any other answer? So we go with the majority. So the answer is going to be 2004. What is the reason? Because the memory in x86 architecture is byte addressable. So meaning what? Meaning that this address that is in here basically is the address for the first element, for the first byte of this element. So it's x2000, the next gonna be x2001 for the next byte after gonna be 2002, 2003, 2002, 2003, and coming to this, then our address is going to be x2004, as your friend has mentioned. Okay, so what's going to be the address for the element after? Okay. I know many of you know this, but just kind of reviewing the material so that Juan, that's the correct answer. Yes, it's 2008. So basically, your answer is incremented by 4, and it goes down onto the last element when you're reading from the memory. So this is good. This is good. Interesting. So this gives you some idea how you initialize your counter and how you increment it when you basically read the data from the section and put it in the memory. One other key questions I have is that assume, okay, let me go back here. Okay. So one other question I have from you guys is this one. So assume that this is the X location and this is the Y location in memory, right? It is the uninitialized section .pss and this one is .data, right? So I want to read from here and put it in here. So what command I can use to take one of these elements? I don't care about the order now. Just give me one command that I can take one of these elements, for example, the first element, and put it in the first element in the .bss section. Is there any command? So how we can do this task? Let's right now think about only moving one of these elements, okay? Not the 10 elements. And then we learn, if we know how to move one element, then we can do the rest for the 10 element, and also we can reverse the order by changing the order of reading in from the counter. Anyone has answered for this? Give me some syntax that they can move one element from that location and move it to the Y location. Assume that the location is X, X, and the location in the .bss section is Y. Just to simplify that, okay? So I have one variable, it's only 1 byte at X location, and I have one variable, it's Y, at basically in the .bss or uninitialized section. I want to move this from X to Y. So what is the syntax for it? Let me go back. Any incorrect answer also will be welcome. So don't think that you have to give the correct answer. So whatever you have in your mind, so how we can do this? Is this possible to say simply move whatever you have at X location and put it in Y location? We said that, let's simplify. So can we write this? And assume that X and Y both are 4-byte lengths, as in this case. Assume that both of them are the same length, 4 bytes and 4 bytes. So the first location in X, first location in Y is Y. Okay, we have some answer here. No, we cannot use it. Okay. All right, I see the syntax from Owen. That's good. And from Jaden. Okay. So Owen, your answer is correct. And Jaden, your answer is not. The reason is that if you remember in one of the lectures, we said that we cannot basically transfer data from one memory location to another memory location without CPU supervision, because these memory are out of the CPU. So anything that is going to move around, so look at it this way, CPU need to know, okay? If you wanna just remember this, they basically, so what you need to do, you need to, so this syntax that Jaden had put in here, move, or my syntax over here, or let's do the dereferencing as well here. My syntax in here is not basically correct, because it's 2 different memory location, and then if you want to do that, the CPU is not there. So if this is a CPU, this is a memory, right? You want something to move. Okay, let me draw this one. This is your CPU, where your general purpose register are EAX, EBX, and so far, and so forth. And this is memory location dot data. We're gonna move some data. It doesn't matter. Even you cannot move the data within dot data. I mean the memory element within the dot data and put it in another location. So basically, this holds for any other thing. So you cannot do the transfer like this. Okay, you have to put it in the CPU. Let me write it in another color. So you have to put it in CPU using general purpose register. Roll it in CPU, and from there you put it back in here. Okay, great. So this is very important. You might have some question like this in your quizzes or probably in your midterm. Okay. So as your friend mentioned, what you need to do is to okay, nice color. So I take X, I assume X is 4 bytes or 32 bits. I choose to put it in register EBX, for example. EBX, and I put that value X. I assume that I define X at the beginning of my program. So this is X. This is the address for the X. For example, X2000. If I say put X in there, it's basically put the address of the memory. So I don't want to add this. I don't want the address. I want the content of it, right? So I need to dereference it. So I put bracket around it. So once I put bracket, means that the content, whatever is the content of this guy, put it in there. The content of this guy is this, like zeros, right? So we put the content in there. So now I have this X placed in the general purpose register in the CPU. Now I can move that data back into the basically other location in the memory. And I use basically another command, move, and this time my memory location is Y, and put EBX. What do I do next? I dereference it. I put the content of EBX into the content of Y. This is my Y, and probably it has address like X4000. And the content is here. I want to put it in that, the content of X2000. Therefore, I use the bracket. Okay, any questions so far? All right. Okay, yes, Yvonne, that's correct. We basically need to CPU to kind of supervise when you're moving data around. Perfect, it's good. Next, let's see what else you should be reviewing before doing the lab. Okay, now we talk about only one element, right? The next time that I want to move the data from X location to Y location, as I said here, I don't care about the order right now. So just think about how to do this movement. The ordering you can basically change by reverse reading the counter value. Now, the interesting part. So what if I want to read the second element from the X location, and I know that the second element is also 4 byte and my first element is 4 byte. How can I basically do this transfer? If you have answer, put it in chat. Wrong or right, doesn't matter. Just try something. So I want to read the second. So I read the first one and put it there. Now I want to read the second one. What should I do? One, two. Okay, I'm gonna wait until I get one answer from you guys and then move forward. So I'm gonna go home earlier, we're gonna drop off earlier. So just try to put some answer in here. I'm not gonna move, guys. Give me some answer. Second element from the data section, assume that X is the array that we define, and we want to put it in the second element in the Y location. Oh, we have something in here from Owen. Owen, this is great. Yeah. Kai, okay, answered 2000. So you are using the direct addressing, and basically As we explained, it's the Kai, your answer is something, but as we explained, CPU has to be involved in the process, and you're using two memory location, so it doesn't work. And also you need to dereference when you put the address in. But thanks for the answer, Kai. But the answer for ON is correct, and really appreciate this answer. I'm happy to see that. Okay, so ON answer is move x plus 4 into EAX, and then move the EAX into y plus 4. That's perfectly correct. Perfectly correct, not good English. Yes, that's good. That's good. We are getting somewhere. We are getting somewhere. Basically, we are working on the lab and understanding the detail of it. This is great, Oren. So move one set. Let's choose the purple color. This time, let's choose another color. Let's choose this. We have a luxury of choosing different. And let's do this. Oh, it's too thick. Okay. So we have move. We want to move that where? We want to move the content of, so x2000. So the value that should be moved is x2004. And we assume that x is pointing to the first element. Therefore, to point to the next element, we have to write x plus 4. So x plus 4, we put it in EDX. And then, so this is EDX, guys. Excuse my writing here, not very convenient. So once we put that in EDX, then we move it to the next element in the array Y, and this is easy. So the next element in that array is this location, right? So if this is Y, this one is going to be Y plus 4. And we dereference it because Y is my address in that location. So I put Y plus 4 and then move EDX into there. That's good. Perfect, Owen, thanks. Now, so what do we do? If we want to move all these 10 elements and then put hard code the memory address, might not be very efficient. You can do this for 10 elements, but what if you're going to move 1 megabyte of data? It's going to be difficult, right? So anyone has any answer for this? So what should we do? Do you remember in your high-level programming languages, we have the concept of counter? You basically define some variable as your counter. And then when you're working within loops, you use that counter, you increment the counter or you decrement the counter to go to the next iteration and do something and do some data manipulation, right? So now I want to implement that. And this time, I want to use register, for example, ECX. Let me use register EDX because ECX can be used in loop as well. So I initialize my EDX with 0, and my intention is to use EDX as my index counter, meaning that, okay, I want to move X. This time it's going to be X plus EDX, and EDX is 0. And the next time I can increment the value of EDX to move to the another elements. Now, give me some answer to use EDX as an index. In here, you see that I use the value 4 as a hard-coded value to move between the memory elements. Now I want to use EDX register as my index register to move between the elements in the memory. Give me one syntax that EDX is involved in this process to move element from this memory location to this memory location. I'm gonna wait. Give me some answer. Okay. This is good, Kai. So, I know the idea behind your code. This is great. That's one of the way to do it. That is good. But can you give me the complete code how to move from one memory location for an array to the other one? So just using these two move syntax. I'm gonna wait. Perfect. This is good, Kai. Yeah. This is great. All right, so we have an answer, so we can move on. Let's erase this one and move on. So let's take it simple. Kai answer is good, but might be a bit advanced for someone that does not know this. So let's take it simple. So assume that we have register EDX and it is initialized with 0. We want to use that as index register. So we first try some simple method than this, and then you can also use Kai, which is a bit more advanced. Okay, so we use the EDX register with 0, then we use move command, and again use the EDX register as an intermediate register for our move, and then we're gonna have X location, we're gonna dereference it using the bracket, and then put EDX in here. Okay, so we do that, that's great. And then we have another move location. This time we're gonna move the content of EDX into Y. We're gonna have Y plus EDX, okay, and then put EDX in there. This is great. And then what? So the difference between this and the Kai answer would be in the way that we increment the counter, okay? So this time, since I'm moving each element from the memory and each element is 4 bytes, therefore I need to increment my index register by 4. Therefore, I use EDX, so I have to use add. I basically use add and increment my, add EDX at 4, okay? So when I do this, so next time, assume that there's a loop over here, right? So there's a loop, you go from here, there to there, and then you jump back up to the first one, and then you repeat this process, right? So this is basically a loop that you're gonna be implementing. So you guys know how to implement that by now. So this is basically you go down and then you jump back, and then you check to see if you do this for the 10 element, and once you do that for the 10 element, you are done, and next time we're going to print the result from the Y location on the screen, and that's it, you're done. So here, the increment is by 4, and I use this index register here. But the way that Kai did it, he has to increment the value by 1 because he does the multiplication by 4. If he put basically 4 EDX in the bracket, therefore he needs to increment its value by 1. So instead of add EDX by 4, it can write add EDX and 1 or increment EDX. So here it is, the way that we move around the things between two locations in the memory. And what you need to do for this is when you take the data from the first location, you need to put it in the last location in your Y array. And then when you read the second location, you put that data back into the last second element in Y. That's only the difference. Perfect. I guess you're ready to do the activity 1. And one thing that I would like to also discuss in here is that in the second activity, let me quickly take a look at that and also share that with you. In the second activity, there is a subtle difference with the first one, but they're almost the same. They're almost the same. Let me do this. Okay. So first activity, we said 10 double word. So 10 double word in here. So let me use different column. Okay. We said 10 double word, and we said in the dot data section, first 5 is 0 and next 5 are 1. And we said that reverse list 10 location in the double word in the .bss, meaning that the data that you define in the dot data section and the .bss section both are double word, the same size. In activity 2, we said that in this activity, reverse 10 words in .bss section of double word with reserved double word and reserved word. Okay. Okay, 10 words. Okay, this time, the reserve location that you're gonna be having is the length of each element gonna be word. Each element in word is, if your element is 1 word, it means that it's 2 bytes. Right now, for the second activity, each of your elements are 2 bytes, okay? But your data that you have defined in the data section, they are 4 bytes. Now we're gonna move something that is 4 bytes and put it in this container, which is 2 bytes each element, okay? So that's the only difference. So you're gonna do the same thing with this difference. So let me again go back to my whiteboard and quickly show you the mechanic of it. And then you guys are ready to start do your program. Okay, perfect. I'm here right now. Okay, now this time my elements in the .bss section are basically, let me delete all of this. Okay, so the difference is this. So I assume that is my memory map. This is my data section where my array goes 0, 0, 0, 0, 0. Each of these are 4 bytes for now. So why 0? Because we define an array of 10 words and 5 of them are 0 and 5 of them are 1. So this is just for an example, okay? It's not, doesn't have any significance. And then we said that now in the second activity, the .bss section, the array that you define it using reserve word. You reserve 10 word in this section, meaning that each element of your array, now it's going to be 2 bytes. So if the length of it is 4 bytes, right? Then each of these gonna have 2 elements for you. Basically, you're gonna have 5 of them. Now, now this is going to be your first element, second element, third, 4, 5, 6, 7, 8, 9, 10. So these are your elements in here, but your basically array elements in here are 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. These are 4 bytes each, but as you can see here, each element in your .pss section are 2 bytes. Now, what you want to do, you want to take this 0, put it in your one of the register, and then move that to the first element in here. Take the second element, put it in some register, and put it in the second location in here. And the third element goes to the third element, and so far, right? There is a change of container in between. You take something that's 32 bits, you have to put it in something that is basically 16 bits. But since my numbers are small, for me, there's not going to be any, error in my computation, because I'm only dealing with 0 and 1, and on 1 bit is enough to accommodate that. I'm just giving it 32 bits for the sake of this lab, and I'm putting back those in 16 bits in the .pss section to tell you how you can move around the data from one location to another location, change the size, and work with the data, just data manipulation. Okay, so I'm gonna do this very quickly. So I wanna ask you guys, give me one instruction. Right now we learned how to move between the array locations. This is the same between this and that. But give me one syntax that I can move one of these 32-bit word and put it in another memory location, which is 16-bit word. And now we assume that the data that is in this location are moving are maximum 16-bit. So there is no computation error doing that. So that's our assumption. Give me one syntax to do this, and then we are done for this basically lecture. I'm gonna wait for your answer. And once I get your answer, we're gonna be moving forward. Hallelujah, we have answers. See, okay. Okay, so Owen, what we want to do, we want to move one element from the .data section, which is 4 bytes. This is regarding to second activity. And put that element in the .pss section where each element defined as 2 bytes or 1 word. So we're going to move one double word into 1 word. 4 bytes into 2 bytes. Assume that there are some number in 4 bytes for the first element here, for example, is 0. We want to take that 0 and put it in another memory location in .pss section, which is the length of it is 2 bytes or 16 bit. So give me some syntax to do that, some move syntax to take the data, put it somewhere, and then from that somewhere, take that data, put it in the memory location. All right. Sure. I'm going to explain that, just waiting for one other person to participate. Okay, Mark is giving some answer. EDX plus X to EDX, EDX to Y plus ECX, EDX at 4, ECX at 2. Okay, one thing that I want to tell you guys, so when you're moving data from one location to another location or between register, your source and destination should be the same size, right? If you're moving data from one memory location, for example, which is Word, and you're putting it in some register, so make sure that these are almost the same size. The answer from Dominic works, but to be consistent, I would like to make this systematic, telling you when you're moving data from the source and destination, try to make it the same size because sometimes you get error. And just follow this for all of your programming in assembly. Okay, perfect. So we have some answers, some right and some not right. Kai, your answer also is fine, but I'm gonna provide one of the answer which is also good for kind of elements. We call it element truncation probably, or element resizing. Okay, let's do this. So I take my X value from here, which is 4 bytes. Oh, what did I do? Okay. So this is the first element, is 4 bytes. All right. So we want to move this into the 2-byte location in here. So that's our goal for these questions. So we said that CPU has to be involved. Therefore, we use basically move. I don't like this writing. Let's move it. I guess raise it again. Okay. So move one of the memory element in X array, which is 4 bytes, and put it in, for example, EBX. You can use EAX, that doesn't matter. I choose to use X and dereferencing. So we assume that we are incrementing X by 4, okay, for consistency. Now, what happened in here is that I have 4 bytes of data or 32 bytes of data, right? And I have my EBX register, right? So EBX register is basically 32-bit or 4 bytes, okay? And we know that the lower part of it is BX register, and there is a higher part of it also, which contribute to EBX. So BX register is the first 16 bits of the EBX register, right? So once I put my data into EBX register in here, then I do the truncation over here. So basically, so I put my data in here. What is that? Okay. I put my data in here. So what I want to do in here, I put my data in here in EBX, and I want to make it a 16-bit data, meaning that I want to throw away the higher 16-bit of it. So what I do is just take this and put it out. So when I put it out, meaning that I just extract the first 16-bit of it. The first 16-bit of EBX is represented by BX. Therefore, my answer is going to be this. Then move BX into Y location. That's it. So everything else in the second activity is going to be the same as the first one, except this. You do this element truncation or element resizing with this process, basically, that we describe here. So all other techniques that we explained for the first activity is applied in here. But whenever you do this, just make sure to implement this one. And then when you increment your second element, then it should be incremented X by 4. But when you want to go to the next element in Y, it should increment it by value of 2. Why? Because in my .bss section now, I have the memory element of size 2, not 4 bytes. They are size 2. Perfect. All right, we are done with the technical part of the lab. If you guys have any question, please let me know. Yes, basically, Kai, so we have EBX register, right? If I want to take the 16 bits of it, I take the BX portion of it. If I want to take the 8-bit of it, right, I take the BL section of the EBX register. But the answer for Dominic and yeah, her answer also was correct. But to be consistent for your memory move, try to use the same size in your movement for your source and destination. It's going to make your programming easier. That's the point. For Dominic, her answer basically for this movement is correct, but I guess for incrementing the counter by 4 or 2, probably there might be more syntax involved. Okay, perfect. If you are ready to do the programming now, what I want to do, I want to quickly share the first part of the code with you guys, and then finish this lab. Okay, let me see. comp-162. Cancel. Okay. Let's try this. There we are. Okay. Let's see. What do we have here? Lab 6. What do we have in lab 6? We have lab 6. File 1.87. Okay, guys. So this is first part of the lab. In case you're wondering how we define the data, I do not show the rest of the code just at the beginning of it. Okay, so do you guys see the screen? My Linux screen?
Yes, we can.
Yes, sir.
Okay, perfect. So this is the way that you define the segment.data for the first activity. So basically it's the double word, right? You put 0001111, and then in the .bss section you reserve 10 elements. You basically do not have anything in those elements. You can assume that they're empty right now. But in practice they're containing some random value. So what you want to do, you want just to take these elements and put it, okay, no, I can't, right? Like you want to take these elements and put it in this section in the memory, but in the reverse order. Now there's 00001, and what your task is to make it 11111 and 000. But you need to basically move those into the .bss section. Once you move them, you write one loop command to basically write these on the screen. So, but when you write it on the screen, it is asked from you to write it on just on one line. So, because if you go to your print, if you call the print and write element by element, and you give it basically the new line, it's gonna write 1111. We don't want to print it out vertically. We wanted you to print it out horizontally. So you don't need to put the new line in your printing function. That's pretty much it. So nothing very complex in here. You still can use your auxiliary file. You still can use your .run sh shell command to compile those files, link those files for you, and run it for you. Same. Just this is the thing that you want to do. And okay, so this is it. Let me quit from this. And for second activity, I want to show you also the beginning of the file. It may gives you some ideas so that you know how to start it. Okay, For the second activity, as you can see here, the first part is the same, right? The first part is the same. But the second part right now is reserved word. You see that this keyword, previous one was reserved RESD, and now it's RESW. RESW. Therefore, your container in the second activity is 16 bits. So this is the first part of your program. Perfect. Okay.